Hi, everyone. Welcome. Well, hope you had a good lunch. If you are attending, the best way to hear this is with the headsets that are here because they're probably going to do another talk over there, and you'll be hearing that too. So have the headsets, and we'll be able to pay attention here. So I am going to introduce Cynthia Brand. She is our security expert. She's been in security for a really long time. I'll let her introduce herself more, but I can say in the few years that I've known her that she is the colleague I would most likely go have a pedicure with. She's going to talk about queryable encryption. And then hopefully afterwards, if there's time, she could take some questions. And if not, she'll be here for the rest of the day and be able to answer the questions later.
Yeah.
So thanks, Cynthia.
Yeah, thank you. So I don't have a mic, so put your headphones on. Oh, no, that's okay. I think I'm not supposed to be mic'd, right? Okay, yeah. Well, I am mic'd this way, but you can only hear me through your headphones. If you could save your questions till the end, because I need to put on headphones to hear you. And we'll get going. Like Karen said, Cynthia Braun, Senior Product Manager for Data Security. I am specifically the Product Manager for Queryable Encryption and client-side field-level encryption at MongoDB, but encryption in general I'm involved with. I have been in encryption for 10 plus years. Started out in payments security, and got on to kind of enterprise, and now at MongoDB. So nice to have you all here for the talk. Hopefully you're not too tired after lunch. Okay, so first we're going to go through what's really a Security 101 or an Encryption 101. Then I'll go into an introduction about Queryable Encryption, what it is, explain a little about the journey and the roadmap for Queryable Encryption, get a little into how it works, the what is this magic, talk about client-side field-level encryption versus queryable encryption, what are the differences, what are the similarities, and then a little about how you can try it out, and some key management enhancements that we recently did as well. So, the encryption layers. Moving and storing data across a network is really well taken care of via TLS. So in-flight, in-transit encryption is meant to keep anybody from eavesdropping over the network. But once that hits the server, it's decrypted. That's where at-rest encryption takes over. So while the database is not up and running, you're not actively querying it, at-rest encryption protects that data. At MongoDB, we have a couple different flavors of that. There's the volume level encryption, which any of the cloud providers actually have. It is actually encrypting that volume, that hardware. There's also storage engine encryption, or what we call our BYOK for the encrypted storage engine. And that you can actually provide the keys for. But what happens to that data in memory? So once it's read, when you're querying it, that data is unencrypted. And there aren't a lot of really good solutions for that. And for particularly sensitive fields, that's often a need to encrypt that data. And why do you want to encrypt that data? Why is that important? So when it's unencrypted in memory, authorized or compromised administrators, whether that be a malicious or just a negligent administrator or DBA, or privileged user, does have access to that data in the clear, and like I said, could either be maliciously leaking that or through negligence leaking that data. You could have malware, such as RAM scraping software, that is in there pulling that data in the clear and exfiltrating it out. Process inspections, and people are also oftentimes concerned about cloud providers who do have access, as well as MongoDB and Atlas, do have access to that data in that clear state in memory. Now, there are lots of different operational controls that we have in place and the cloud providers have in place to keep us from actually getting that data, but it is a trust problem because, again, technically we do have access to it. If you encrypt it in use, we wouldn't have access to it. MongoDB doesn't have access to it. that cloud providers don't have access to it. Even your DBAs or your root users don't have access to it. And that is why we built what we called client-side field-level encryption, which is our first in-use encryption operation or solution. But just like I've actually talked to a number of you today about, or in the past, once you encrypt data, you can't really do a whole lot with it, which is why we're introducing queryable encryption. So let me take you through a couple different scenarios. So this is what it would look like if you have either just at-rest encryption or no encryption at all. And say your application needs to find all documents that have the social security number 901104312. It issues a query to the database can parse through all of the data, it sends it back to you and say, this is a 1 million record database of, a billing info, and 10 records matched it. It queried through that quickly and returned it, but that data is not encrypted. So the cloud providers all have SDKs that can do, say, client-side field-level encryption along with some third parties. But that data, once it's encrypted, is not queryable. So what does that look like in that case? So again, your application would issue that query. It would hit the database. Database couldn't figure out what those 10 records were. So you would actually need to pull all 1 million records back into the application, parse through those to find those 10 records. Now it's doable. It's not practical. Mostly because of the kind of performance hits that you'd take by pulling all that data back and doing the filtering on the client side. So that's why we came up with queryable encryption. It allows you to encrypt specific sensitive data fields on the client side. Make sure that those stay encrypted throughout the life cycle because the client is the only place where those encryption keys are available. So it's encrypted in transit, at rest, and in use. That data gets sent to the server and you're still able to do rich expressive queries on that with no crypto experience. And what I mean by no crypto experience is that the query that you issue is exactly the same for unencrypted or encrypted data. There's actually a translation layer that will take your unencrypted query and rewrite it. So you don't have to worry about rewriting your application. You also don't have to worry about taking a large menu item of crypto primitives and figuring out how to apply those in the right order. And the rich expressive queries. So what do I mean by rich expressive? So equality matches, range, prefix, suffix, and substring. So betweens, greater than, less than, equal to, begins with, ends with, and contains. So you can see the query here. It's looking for a 901.104.104.312. The server is actually able to process that fully encrypted data. We are the only platform to implement this fast searchable encryption scheme that allows the server to process, again, that fully randomly encrypted data, return back the documents that match without understanding anything about that data. So when the server receives this query, it's an encrypted query. It doesn't know it's looking for 901.104.312. It doesn't even know that it's looking for a social security number. All it knows is that there are 10 documents that match it, and it's document 1, 5, 10, 12, 14, etc. It returns that data back to the application where that data is decrypted. So let's look closer at what that flow looks like. So again, the query from the authenticated client, and it has to be an authenticated client. You can't have somebody else issue a query and get that result back. Even though it would return back encrypted data only, it still has to be an authenticated client. And that's one of the great things about keeping, like, say, a DBA or somebody else out, is it has to be that authenticated client. So just a regular MongoDB find query on that social security number. Here's the second point that keeps unauthorized people out. Is it hits that MongoDB driver. That MongoDB driver knows that that field is encrypted. it will go and ask for the encryption keys from the customer provided key provider. So this is a cloud KMS, an AWS KMS, Google's Cloud KMS, or the Azure Key Vault. It could also be that you have an on-prem HSM, and as long as you've got a KMIP-enabled HSM, we can grab it from there. You could actually do it across cloud, so have your data in AWS and your keys in GCP. Or you could use what we call a local key provider, which really you should only do for development. But we essentially don't care where you're getting that key. We're fairly agnostic to that. We just need that key back. So the MongoDB driver, again, sits within your application environment, and it will perform encryption and decryption. So it sends that encrypted data over to the server along with, it says encrypted search key. It's not a key like an encryption key. It's more like a token, but not a token as people generally think of it. It is a piece of cryptographic information that tells the server which documents to retrieve. That server processes that data. It finds, again, just those matching documents. You can see by the orange values that these are randomly encrypted. This is not deterministic encryption where the ciphertext is the same every time. It actually has different ciphertext. It returns that back to the MongoDB driver, does the decryption, and returns that data to the application itself. Okay. So this is a screenshot of what we have, our Compass GUI. So if you're not familiar with Compass, it is the UI for MongoDB. And we have configured it to both show what it would be like for, say, a DBA that doesn't have access to keys and the application, and then one that does. So right here you can see mobile, date of birth, social security number, card type and expiration all have asterisks. That's just how Compass shows encrypted data. And this would be essentially what it would be like if a DBA without the appropriate access tried to query that data. Now for an application that has access to the keys and is authorized, you can see that data is now in its clear text where you see the little keys next to it. So what are the use cases for something like these rich encrypted queries? So financial services, say there is a bank application and you're looking for fraud detection. A range of dates is a common way to query for that. Dollar amounts. So these are where a greater than less than can work, where you've got fully encrypted data and you can find all the transactions between those. For suffix, the last 4 digits of a social security number, those are the non-sensitive parts. So, you know, you call in, somebody asks you for your last 4, call center person can put in the last 4 digits, search, and get back that encrypted data. Healthcare, also similar. People misspell my name all the time. You can just type in a couple letters of somebody's name and get back all the results. So let's go through kind of the key benefits. So what are the, why did we build queryable encryption? The rich querying unencrypted data is obviously the big thing. It's being able to do beyond an equality deterministic match. It's being able to actually use that data in its fully encrypted state. The end-to-end fully randomized encryption. So it is encrypted at the application and only ever decrypted back at the application. So any network, it's encrypted over while it's stored in the database server, while it's being used in the database server. It is fully encrypted. So although this is groundbreaking query technology, we're using standards-based cryptography. So this is all NIST standard cryptography, AES 256, HMAX, and SHA 256 as well. This is FIPS compliant. We didn't come up with our own encryption. This isn't a roll your own thing where we invented new primitives. These are strong technical controls for critical data privacy use cases, whether it's a GDPR or a PCI, or we're in California, so we got CCPA. these often have a higher bar, and you can use these as technical controls, not just operational controls, technical controls to ensure that that data is not being exposed. And faster app development. Like I mentioned, you actually don't have to change your application to write or to get these encrypted values. There is a translation layer at the MongoDB driver that will rewrite your query to an encrypted query, so you don't have to change that application. There is just a setup. And we have spent the last 18 months building it, making it intuitive for developers to use, again, by doing that translation. Also, like I mentioned earlier, this is not a you have to figure out how to implement your own encryption. This is a fully baked encryption solution. You configure it, it will do that encryption for you, and we have key management and key rotation all built in, which I'll talk about in the last slides. And lastly, reducing institutional risk. You know, one of the big concerns about moving to the cloud is my data secure? Again, with these strong technical controls, you can be confident storing your data in MongoDB because that data is actually just the encrypted data. You're not storing clear text data in MongoDB. So now the part that everybody wants to know about, which is what is this magic? So the security model here is what we call multi-snapshot secure. So a snapshot adversary is a person that can come in and take a snapshot of the data in the database, any keys stored in memory, CPU state, logs, etc. So a point-in-time snapshot. They can even do multiple successive point-in-time snapshots. With those snapshots, they cannot decrypt that data. They cannot do inference attacks on that data like you can with deterministic encryption as well. So the formal security guarantees, again, I talk about this being fully randomized data. It's verifiably CCA, so chosen ciphertext attack secure. The ciphertexts don't reveal anything about the plain text, which is what happens in deterministic encryption if you have low cardinality or a low number of values. What they can tell is the encrypted document size. The encrypted indexes also are the same verifiably adaptive multi-snapshot secure. And I'll talk about the encrypted indexes in this next slide so you understand the difference between the two. So the boring part, the document, the actual data fields that you're encrypting are encrypted with AED, which is an authenticated mode of AES encryption. So we use the encrypt then MAC using AES CTR mode 256 and these HMACs based off of SHA-2. Like I said, the decryption and encryption only ever happens at the client in your application, so that data is never in the clear outside of it. There is the key that we get is actually broken into 3 keys, so you give us 96 bytes of data. We take those first 32 bytes. That is your actual AES encryption key. The second 32 bytes is your HMAC encryption key. And after that, it is a key that we use for these encrypted search operations to build these encrypted search indexes. Key management is like it is in client-side field-level encryption as well. We use what's called envelope encryption. So we take a customer-provided key and use that key to encrypt the data encryption keys. Those encrypted data encryption keys are what gets stored in the database. The database never has access to that raw key material. It cannot decrypt those keys in order to decrypt the data. Only the application can. And like I said, we're fairly agnostic to what the key provider is. It could be one of the cloud providers. HashiCorp Vault has a great KMIP that we integrate with. You could have a custom key service if you're a bank and you have a ton of HSMs, and as long as they have KMIP protocols, we can interact with those. Okay, so here's the interesting part, the new part, which is these functional search indexes. So this is based off of an encryption scheme called structured encryption, and it has been researched in academia for 20 plus years, but never in industry until now. So the way that it works is it allows the client to be stateless, and the database maintains that blinded state of the encrypted data. It is, oops, okay. It is meant for a distributed, highly available, highly scalable database by design. When we implemented it in MongoDB, that was one of the big requirements. The scheme is robust to client failures, high contention of sessions, drop sessions, et cetera, which is why we have to have the stateless client. Like I said, it's based off of a well-researched thing called structured encryption that uses data structures called encrypted multi-maps. These are an inverted index that actually has a label and then a bunch of values of essentially the documents that match it. Those labels are pseudorandom functions, which are actually HMACs in this case, actually chained HMACs in this case. And it allows for fast, efficient lookups. Forgot to mention about those HMACs. People hear HMAC and they think of a hash. It is absolutely not a hash. This is a keyed, a secret keyed value. It's a secret keyed hash, and again, the database doesn't have the keys to be able to decrypt that hash. So how is it different from other solutions? Because generally when people hear about encrypted search, they think of homomorphic encryption or secure enclaves. Like I said, we built Queryable Encryption and Structured Encryption specifically to be able to be used in highly distributed, highly scalable databases for real-time database operations like MongoDB customers need. It's a software implementation, it's hardware agnostic, so it doesn't matter what we're running on. And it is optimized for sublinear searching, which is why you can get better performance than some of these other solutions. Homomorphic encryption being the one that is has the most performance implications. So it is not natively offered in a general purpose database. It is actually very slow for something like encrypted search. So homomorphic encryption actually requires essentially a full table scan and then computation on top of it. So it is very well suited for arithmetic operations and things that don't need to be returned in real time. But for something like a real-time encrypted search, it's a pretty poor solution. Secure enclaves are also quite popular. And you hear a lot about those. They're often cloud provider proprietary, so there's specific hardware it has to be run on. The keys, although they're only ever exposed within the secure enclave, are actually available to the cloud provider or the hardware provider, so the customer doesn't manage those keys. And enclaves, because again, they are specific proprietary hardware, they are not as powerful as general purpose CPUs, which is what we use. So let's talk about CSFLE, which if you don't know about client-side field level encryption, you should definitely look into it because there's still a lot of applicability there. And then queryable encryption, what are those differences? So one of the big questions we get is CSFLE being deprecated? And it is not. Like I said, there are still a lot of use cases where CSFLE is a great solution, if not a preferable solution. There is no current way to migrate CSFLE to queryable encryption. So if you have CSFLE already implemented, keep that implemented where you are. Any new collections, you can use queryable encryption. We will have a migration path in the future, but again, right now we're in preview for this. It's not supported, but like I said, that is planned. So really, queryable encryption should be used for net new only. And it must be specified when you create the collection. So how are they the same? Both provide the highest levels of confidentiality and integrity. Again, these are authenticated AES 256 solutions. They both have queryable and non-queryable options. CSFLE, you can do random encryption or you can do deterministic encryption. Now, deterministic encryption is still a very strong encryption solution if you have high cardinality data. If you have a piece of data where there are 5 possible values, that's when something like deterministic becomes subject to something that are called inference attacks. So if you were to encrypt the eye color of everybody in the world, about 80% of people's eye color in the world is brown, you would see that same ciphertext 80% of the time. That's an example of an inference attack. You would know that we're brown. If you were to encrypt people's social security numbers or a random ID number, there are a lot more of those values, so inference attacks aren't really a problem there. But queryable encryption allows you to do an equality encryption, like an equality comparison like CSFL does, but on fully encrypted data. So it's a different ciphertext every time, never subject to an inference attack. They have, like I said, it's the same AES 256 with authentication encrypt than Mac. They have common key management features, so the same KMSs, the same key sizes, the rotation, migration, all of that is supported. The encrypted data is stored in a field as what we call a bin data field on both solutions. So there's not any difference there. It is those structured indexes that is different. We also have something, if you are familiar with CSFL, called the shared library that we recently introduced. It replaces what was called MongoCrypt-D. MongoCrypt-D had some difficulties there were some difficulties deploying it. It had to be run as a daemon. The shared library does not, and it solves a lot of those problems. So I don't see anybody cheering, so probably none of you have run into the problems, but it does make things a lot easier. CSFL and Queryable Encryption are both client-side encryption. In CSFL, the server is largely unaware of CSFL, whereas in Queryable Encryption, it really is integral. Oh, 3 minutes? Oh, wow, okay. Wow, sorry guys, I am way behind. The things I will mention, there is additional data. So there's a new field that comes up, and there are 3 new encrypted collections that come up with Queryable Encryption that are stored server-side. If you try this, do not modify any of these. This will not only kill you, but it will hurt the entire time you're dying. If you modify those collections, if you modify that additional field, you will not be able to query your data. Quickly into the trade-offs. FLE is very fast. It just does encryption, decryption, whereas Queryable Encryption has these additional data structures and these indexes that it has to build, so it is slower. However, you have more queryability. So instead of just equality, you have equality, range, prefix, suffix, and substring. I will go through these because these are really important. These are preliminary numbers. The performance, the reads are very, very fast. Sub-millisecond. Writes are slower. So 1 write on the client side is multiple writes on the server side. So if you have a low volume, you see a negligible impact. If you have a high volume and you're trying to do batch kind of inserts, 5 to 10 times the hit. So if you have a high write application, this might not be the solution for you, at least right now. We're doing more tuning, but because, like I said, there are multiple writes on the server side, it is slower on the write side. Storage, because again, we're storing these 3 collections on the server side, there is an impact to storage. So you can get 2 to 4x, 2 to 4x the storage. That's for any encrypted document. So if you have 1 encrypted field, you're probably not going to see 2 to 4x. If you have 10 encrypted fields, you might see a little more. Again, because we have to store more information on the server side. Journey and Redmond, I can do this. Okay. In 2019, we introduced client-side field-level encryption, like I talked about. 2 of the gentlemen that we had do reviews of client-side field-level encryption were pioneers in encrypted search. spun off a commercial arm of theirs called Oroki Systems, and we were able to acquire them. So not only did we acquire the technology, but we got the two guys who founded it as well. A couple months ago, they actually formed an advanced cryptography research group at MongoDB, so not only working on encrypted search, but other privacy-enhancing cryptographic technologies, which you'll see after I let them actually do more research when we get prefix, suffix, and substring in. So we announced in preview equality at MongoDB World. The next will be range. After that, prefix, suffix, and substring. What's in public preview, the crypto framework, equality comparisons, and our Compass UI, which actually you showed earlier. You can test it. It's available in the 6.0 release, but it is for evaluation only because it is in preview. We may introduce breaking changes, so don't put your production workloads on it. Like I said, we're doing those. Key management enhancements, I got 8 seconds, I'm gonna do it. Okay, key rotation. Previously, that was more of a manual process. Now we have a quick API that you can call. It will rotate your entire key vault without your application being impacted. Key migration, again, another API call. You can actually move, say, from AWS to GCP, your key, again, without impacting your application. And custom key management. If you have the need to, like some banks actually have the need to produce their keys in an HSM and then import them into, and then use those for encryption, you actually can do that now. So if you need to be able to, because of regulatory issues, create a key in an HSM, you can actually use that as the data encryption key for Queryable Encryption and CSFL, all these key management enhancements. Apply for both. And how can you try it out? 6.0 server, you have to have a Queryable Encryption aware driver. Like I said, we have that new shared library that if you have Atlas or Enterprise Advanced, you can use. If you want to use what we call Explicit Encryption, where you actually do change your application, that's Atlas, Enterprise Advanced, or Community. I'm going to go past that. Oh, and that is it. Thank you all very much. Appreciate your time.
Thank you, Cynthia. I imagine people might have questions, but we'll have to do them. I'll give you guys a break, and maybe we could take the questions off on the side here if you do, please.
Okay, sounds good. Yeah,
Thank you,
thank
Cynthia.
you, everybody.
And she's really good, like for me, when she explains security to me, is like the one-on-one conversations where she helps me understand where I am and how to get where she is. So thank you, Cynthia. And please rate and review, and any feedback about how to make it better or things you want to learn more about would be awesome. Thank you.